Good morning, students. So, today we shall discuss the concept saddle point. That is, in the previous video, we have already discussed the conditions that have to be satisfied for the optimization multivariable function. That is, if suppose you are given a function z is equal to f of xy, for a function to be at its relative maximum or at its relative minimum, three conditions have to be satisfied. The first condition to be satisfied is that the first order partial derivative of the function with respect to each of the independent variables must be equal to 0. That is, dou z by dou x must be equal to 0 and dou z by dou y must be equal to 0. And the second condition to be satisfied is that is dou squared z by dou x squared and dou squared z by dou y squared must be less than 0 for a function to be at its relative maximum. And also dou squared z by dou x squared and dou squared z by dou y squared must be greater than 0 for a function to be at its relative minimum. Now, in the case of multivariable function, in addition to these two conditions, there is a third condition that also must be satisfied. That is, the product of the second order direct partial derivatives must exceed the product of the second order cross partial derivatives. So only these three conditions are satisfied. We can say that the multivariable function is at its relative maximum or at its relative minimum. Now we are going to examine what happens when the third condition is violated. Okay, if you are not able to satisfy the third condition, what happens? Okay, now that in that case we come across what is known as saddle point, or sometimes it would be inflection point. Okay, either we'll be having a saddle point or we are having an inflection point if the third condition is violated. Now first we shall examine the saddle point. That is, of course, we know that the third condition that has to be satisfied is that is dou squared z by dou x squared into dou squared z by dou y squared, that must exceed. That is the product of the second order direct partial derivatives must exceed dou squared z by dou y dou x into dou squared z by dou x dou y. That is, must exceed the product of the second order cross partial derivatives. Suppose if this is not satisfied, okay, if this condition is violated, either we have a saddle point or an inflection point. Now, in the case of saddle point, we can say that what we can observe is that these two would be in the that is different directions. Okay, these two would be having this different signs. That is, dou squared z by dou x squared would be having a sign that is different from dou squared z by dou y squared. That is, for example, if this is positive, this would be negative. Contrary to that, if this is dou squared z by dou x squared is negative, then dou squared z by dou y squared would be positive. So that is what we can say about saddle point. That is, the third condition would be violated. And not just that, in the case of saddle point, we can observe that these two would be having two different signs. Okay, if dou squared z by dou x squared is positive, in that case you can expect dou squared z by dou y squared to be negative and vice versa. Now, using the help of this figure, we are trying to explain the concept saddle point. Let us see what saddle point is. Here also we have a three-dimensional space. Of course, we have z axis, then we have x-axis and y-axis. And this is the diagram that we are examining. And of course, let us consider, or let us start with the point S. And S is supposed to be a saddle point. And when you drop a perpendicular from S to the floor, of course, you know that the value of X is X0 and the value of Y is Y0. Now, S, it happens to be at the meeting point of two curves. You have curve A, B, and you have curve CD. So, you have two curves A, B, and you also have a curve CD. And these two curves meet at point S. And at S, we know that the value of X is X0 and value of Y is Y0. Now let us consider the movements of that is movements from point S along these curves. Now let us first take the curve let us take the curve, for instance, CD. Okay, let's take the curve CD. Let's take a movement from point S to a point on the curve CD, that is to the point D. Okay, from S you are actually moving to point D along this curve CD. Now when that happens, we know that there is a, of course, at S we know that the first order partial derivative that is of the function with respect to x and with respect to y is equal to 0. The first condition is satisfied, isn't it? At S, of course, we know that the first condition, that is dou z by dou x is equal to 0 and dou z by dou y is equal to 0. The first order, that is partial derivative of the function with respect to x and with respect to y is equal to 0. The first condition is satisfied. Now we are considering the movement from point S to another point D along this curve CED. Now when that happens, of course, we know that this is happening because of the change in x, isn't it? Because when you move from S to D, when you look at the foot of this perpendicular, we know that y is constant at y0 and it is a value of x that has changed. Let us say that x0 dash. Okay, the value of x has changed from x0 to x0 dash, while the value of y is constant at y0. So basically, when you are considering the movement from S to D, basically you are taking what is it, dou squared z by dou x squared, isn't it? That is, you are measuring what is it, dou by dou x of dou z by dou x. That is, of course, what is happening to the dou z by dou x when x alone changes, when y is constant. Now, of course, when you look at the slope, it is very obvious that it is rising, isn't it? So definitely we can say that this is greater than 0 because it is obviously it is increasing. We have an increasing slope as you move from S to D. That is, when you take dou squared z by dou x squared, it is greater than 0. Similarly, if you take the moment from S to C also, you are moving along the same curve CD from S to C. When you are moving, basically you are taking dou squared z by dou x squared because at the foot of the perpendicular here also we can say that the value of x is changing. It is x02 dash. Okay, there is a value of x has changed from x0 to x02 dash, while the value of y is constant at y0. Now in this case also we can say that when you take the dou squared z by dou x squared, when you move from S to C, the slope is rising, so it is greater than 0. So here we can say that the second order direct partial derivative with respect to x is greater than 0, and that is something that we can actually observe here, right? But in the case of saddle point, earlier we have mentioned that the third condition will be violated and the dou squared z by dou x squared and dou squared z by dou y squared would be having different signs, isn't it? If this happens to be positive, then this should be negative. So that is a case of a saddle point. So we have observed the movement along CD when you move from S to D or from S to C. Of course, we are taking dou squared z by dou x squared, then that is greater than 0. Now let us see what happens when there is movement along the curve AB. Okay, let us consider movement from S to B or from S to A. In that case, what is happening? Let us examine that. Okay, now when you take the moment from S to B, of course, it is very obvious that here, of course, we know that the first condition is satisfied at S. That is dou z by dou x is equal to 0 and dou z by dou y is equal to 0. But when you move from S to B, basically you are measuring what is the dou squared z by dou y squared, or you are taking dou by dou y of dou z by dou y, isn't it? Because you're moving from S to B, which means that here the value of y is changing while the x is constant at x0. That is at B, you know that the value of x is x0 and that is the value of y that is altered. The value of y, it is actually y0 dash. Now, when you move from S to B, what is happening here? The slope of dou z by dou y, that is slope dou z by dou y or dou by dou y of dou z by dou y. That is when there is a change in y alone holding x constant, dou z by dou y is actually decreasing as you move from S to B, right? And similarly, as you're moving from S to A, as you move along the curve AB, as you're moving from S to A, here also we know that when you observe the point on the y-axis, of course y has changed, it is now y02 dash, but the x is constant at x0. So here also when you are considering the movement from S to A, here also you are taking dou squared z by dou y squared, or you are seeing what is happening to dou z by dou y when there is a change in y alone holding x constant, and in that case also we can say that the slope is falling, isn't it? Dou z by dou y is actually falling. So we have a this less than equal, less than 0, isn't it? Dou squared z by dou y squared is less than 0. So just as we have seen in the earlier case, the third condition is violated because these are actually moving into different direction. That is, you cannot say that here just by looking at this or just by looking at this, you cannot say that either you are at a relative maximum or at a relative minimum, because these two are actually moving in this will give you two different, the change in slope that is actually different. That is as you move along these two different curves, that is as you move along AB, that is from point S as you move along the curve AB, it indicates that dou squared z by dou y squared is less than 0. But on the other hand, when you are moving along the curve CD from point S, either you may move to D or to point C. In that case, it indicates that dou squared z by dou x squared is greater than 0. So in that case, we can see that the third condition of maximization, minimization, or optimization is violated, and not just that, that is, if dou squared z by dou x squared is positive, contrary to that, you get a negative dou squared z by dou y squared. So these two would be having two different signs. So when there is a saddle point, what you can observe is that the third condition would be violated, that is dou squared z by dou x squared into dou squared z by dou y squared. It will be less than dou squared z by dou y dou x into dou squared z by dou x dou y. So this would be violated. Actually, this has to be greater than, isn't it? But this would be violated, and not just that, these would be having different signs. If this is positive, then this becomes negative, or if this is negative, this becomes positive, right? So that case is called saddle point. So in order to make sure that this particular point is not a saddle point, we have to get this third condition correct. Only if this third condition is satisfied, we can state with certainty that we are actually having a critical point at which the function is at its relative maximum or at its relative minimum. I suppose this is clear to you, students. Thank you.